Hello and welcome to your channel, Your Diary. Today's topic for discussion is isostasy. I've generally noticed that students will have a lot of confusion regarding this topic. So I will try to make the lecture as simple as possible, and I'll give you a holistic storyline so that after the lecture is over, you have no more confusion. So let's start with the topic. The term isostasy was coined by an American geologist whose name was Dutton, D-U-T-T-O-N. Dutton, and he gave this term way back in 1859, but he did not develop the concept. He just gave the term isostasy. Now in point number 1, let us try to define the term. Isostasy simply means the mechanical stability between the huge upstanding mountains, plateaus, etc., and the very low-lying basins on the rotating earth. So if I try to explain this with a diagram, see, on the earth's surface we see great heights of mountains. Let's say Everest, almost 9 kilometers in height. Then we see several plateaus which are smaller in height, and then there would be plain areas, and then the great depth of ocean basin. Okay, now geologists have seen that it is not as a part of a destiny that these different kind of rock features of several heights are existing side by side. They say that there are certain physical laws which are maintaining the mechanical stability between them. Okay, like if I give an example, if the miners who would go into the coal mine or the mineral mines, if they blast off a part of a huge mountain with the help of dynamite, there can be severe earthquake. Okay, it shows that these several features are maintaining a very delicate mechanical balance. Now in point number 2, we see that this idea of isostasy slowly developed during various geodetic surveys from time to time. For example, there was a survey in 1735. That survey happened in Andes Mountain in South America. And then there was another survey in 1859, which was done in the India's northern plain, that is Indo-Gangetic plain. And this survey was mention worthy because this was done by Sir George Everest. He was the Surveyor General of Geological Survey of India, and he was doing this survey. And these people found out something called gravitational deflection anomaly. I will explain this term to you. They found something called gravitational deflection anomaly, and based on that they slowly developed the comprehensive theory of isostasy. During our discussion, we will read the theories, we'll discuss the theories of Sir George Airy, theories by Archdeacon Pratt, theories by Hayford and Bowie, by Joly, and in the end, the theory by Hess. Okay. Now let us try to understand what is this gravitational deflection anomaly, which explains the theory of isostasy. To understand the gravitational deflection anomaly in detail, we have to discuss the 1859 survey of the northern Gangetic plain under Sir George Everest. During this survey, the surveyors were trying to find the latitudes of two places. Let us say one was place A, another one is place B. To find the latitude of these two places, those people were using two different methods. Listen carefully. The first method was named direct triangulation method, and this is a simple pen and paper method, mathematical method. Okay, and to cross verify this result, they were using another method which was known as astronomical method, and in this astronomical method they were using this plumb line or the plumb bob. But very surprisingly, almost always the results were different. What they were getting in triangulation method and what they were getting in astronomical methods differed. But the surveyors readily understood that this difference is coming because of the gravitational attraction force of this huge mountain called Himalaya nearby. They understood this. But now the question was then how to subtract this gravitational attraction force of Himalaya. They decided, why not to calculate the attraction force of Himalaya mathematically? And they did that. They took the average density of Himalayan mass as 2.75 gram per cubic centimeter. They took this and they calculated on pen and paper the gravitational attraction force of Himalaya, and then they tried to subtract it from here. But the bigger surprise was here. They found that after calculation, the gravitational attraction force that they found is actually much larger than what they were finding here. You understood the point? Astronomical method was giving a different result. Why? Because of the gravitational attraction force of Himalaya. So the surveyors thought, let us calculate the gravitational attraction force and subtract it. But when they calculated, they saw that the Himalayan attraction force should have been much higher, but it is actually not so in reality. So this was the gravitational anomaly that they found, and this anomaly led to the birth of theory of isostasy. Slowly we will discuss how. When it was found out that Himalayas were not exerting as much attractional force as it should have been according to its size, then people started thinking that probably the Himalayas are hollow and are composed of air bubbles and there is no rock inside. But then it was Sir George Airy who postulated that no, it is not that the inner part of the mountain is hollow. Rather, he said the excess weight of the mountain is compensated or balanced by lighter materials below. That is, he gave a concept of root formation for the mountains. According to him, the crust of relatively lighter material is actually floating on the substratum of denser material or sima. In order to prove his concept, Airy took several pieces of irons of varying lengths and put them into a bucket full of mercury. These iron pieces sunk into varying depths depending on their length. You can also visualize, if you take the different iron pieces and put it into mercury, what will happen. I'll give you a diagram to make this more clear. So this was what Airy experimented. You can also visualize, if you take such iron pieces of varying length and put it into a basin of mercury, then they will get submerged into different depths. It is something like a boat floating on the water, right? Now I will draw the real picture on the earth's surface, the mountain and its root formation. Okay, you try to match with this diagram. So according to Airy, the real scenario is this. If this is the huge mountain, sialic mass, you know that mountains are made up of sial, then there is also a sialic root deep into the mantle, and this is the root. Now if you take an example of plateau, which is also made up of sial, then there would be a much larger root of the plateau, and then plain, and this is the ocean bottom. This is also a sialic mass, and this is the root. Okay, and Airy was actually trying to explain that why the Himalayan attraction force was very less despite Himalaya being of such enormous size, and he said it is because the Himalaya was made up of sial. Okay, that is silicon and aluminium, both are lighter material, and then there is a larger root which is again made up of sial. So if this huge mass with a root is both made up of sial, and in this column he gave this concept of column, okay, the rest part is sima. You understand, this is sima because the sialic root is submerged into simatic mantle. So he said that in this column only this black part is heavy sima, that is magnesium and silicon, that is mantle material, and rest part is lighter sial. So if you bring a plumb bob here, how come this sialic matter will attract that more? No, it will be less attraction, and the simatic mass is less because of this root. But then if you consider this column where there is plateau, see, this root is smaller, so much more simatic magma is here in this column. So he wanted to say this plateau column will attract the plumb bob more, that is, the attraction of a plateau will be more than Himalaya. And then if you come to this plain, and see this column, it is so much mantle material, that is Sima. So this plane will attract the plumb bob more, the attraction force of plane will be more. And if you see this column of ocean floor, then it is mostly magma, Simatic magma. Okay, so this column will have even more attraction force. So be very clear, although the size of Himalaya is huge, its attraction force will be low. Why? Because the magma material, the heavier material, is low because it has a huge root. But if you see the basaltic ocean floor, the attraction of this ocean floor will be very high because this column has mostly Simatic magma, which is heavier, okay, and the root is actually smaller. So this is the concept. So one thing must have been clear by now while we discuss the George Airy's theory, that why the large Himalayan mass gave the gravitational deflection anomaly. Because as you see from the diagram, that Himalayan root is very big, it's a large root, and it is a cealic root, that is, it's a lighter material, and as the root is so big, it has displaced most of the magmatic materials, okay, and the magmatic material, that is the Simatic material, which is left into this column, is very less, only this much, the heavier material. And that is the reason the Himalayas showed gravitational deflection anomaly. So in a single line, more the Simatic material, higher will be the attraction. So here the Simatic material is very low. That is why Himalayan mountain showed lower attraction. But when they measured in the plain area, here you see the magmatic material is very high compared to the Himalayan column. So when they measured with the plumb bob in the plain area, it showed greater attraction force, which is very normal from this diagram. So by now you must have understood that George Airy's theory is based on Archimedes' principle of flotation, and Airy also compared his theory with a floating boat. He said that Himalayan mountain, or maybe the plateau and plain, etc., are actually like a boat floating on the water. So heavier the boat, the more is the luggage, the more will be the submergence. And just compare with the boat full of lot of luggage, so there will be lot of submergence. The boat will dip into the water more, and if you throw away the luggages one after another, the boat will come up. Now let us use this boat analogy to understand how the geologists will find mineral oil, or say gas, etc., in the ocean bottom. We all know that India's shoreline is very rich in mineral oil, gas, etc. Let's say the Bombay High region off the west coast of Mumbai, where there is a rich reserve of mineral oil. Let us say that this is the west coast of the Bombay, and this is the Bombay High region where there is a source of mineral oil. Now we will use the concept of flotation, and we will try to explain that how the gravitational deflection anomaly in a gravitimeter tells the scholar that there is oil in the ocean basin. The idea is very simple. As there is a source of oil which is lighter in weight, so the overall weight of this oceanic plate is lighter now, so its root will come up, the concept of flotation. So the newer root will be like this. So this much portion will now be occupied by heavier magma, whereas magma was earlier here. Now this magmatic layer has come up over here to occupy this place. That is how, when there will be a gravitimeter brought by the geologist over this area, it will show an anomaly, or rather it will be attracted more, and they will understand that there is a accumulation of mineral oil. Only this much understanding is enough for us. Now it is time to sum up the concept of Sir George Airy, and while discussing that, we will see that isostasy as a theory did not develop in a single go. To some extent, the concept of Sir George Airy was true, and he also went wrong in some areas. And I will discuss that in 3 points. Point number 1 is Sir George Airy proved his concept taking the materials of the same density, that is the iron pieces of varying length. I already explained that in the previous slides. You can go back and check. He took iron pieces of varying length and put them into a basin full of mercury. And these iron pieces sunk up to varying depth. And that's how he drew an analogy with this Himalayan plateau, plain, etc. So, his concept is also known as uniform density with varying thickness. This particular phrase, that is uniform density with varying thickness concept, must be there into your answer sheet while you are discussing Sir George Airy. Now, what is the meaning of this uniform density? You can always refer to this diagram. He used all iron pieces, right? But they are of varying length. See, the lengths are varying. And as the lengths are varying, so the weights are also different. And according to their weight, they have sunk into different depth. It has sunk up to this, it has sunk up to this, it has sunk up to this, etc. And you can see the same analogy here. As the Himalayan height is too high, its root is very big. Plateau height is less, so its root is of less depth compared to Himalaya. So is with plain and the ocean bottom. Hence the idea, uniform density with varying thickness. George Airy took the density of all the cealic masses, that is this cealic mass, this cealic mass, this and this, as the same 2.75 gram per cc. And it is very clear that here he went wrong, because the whole density of the huge Himalayan mountain and its root deep into mantle cannot be the same. Same with the plateau and the plain and the ocean bottom. We all know, we have read the series like P-bag, okay, peridotite, basalt, andesitic, granitic. So many various minerals are there into this huge mountain column, so their density cannot be the same. And also in his theory of flotation, Sir George Airy said that for every 1/10th part of the crust above the surface, there would be almost 9/10 of it beneath the surface. So in that sense, if we take the height of Himalaya as almost 9 kilometer, so according to George Airy, 9 times of it, that is almost 81 kilometers, will be the root formation, which is utterly impossible, because we all know that there would be 1 degree increase in temperature every 32 meter of depth. So if you go 81 kilometer below the mantle, there will be huge rise in temperature, and in that temperature no cealic root can exist. So in the end, we can conclude that although Sir George Airy is criticized on these very points, but his concept of root formation and his concept of flotation were nonetheless very true. Now, once we are done with the theory of Sir George Airy, let's move to the next scholar, who is Archdeacon Pratt, and we will see that how Pratt gave an altogether new dimension to the theory of isostasy. Sir George Airy said that the density of the mountain and its root, the density of plateau and its root, etc. and so on, are the same, and he took it as 2.75 gram per cc. But Pratt begged to differ in the very beginning. He studied the rocks and their densities of the Himalaya and the neighboring plains and etc. And he found that the density of each higher part is less than the lower part. That is, Pratt found that the density of mountain is less than the density of the plateau. Density of the plateau is less than the density of the plain. The density of the plain is less than the density of the oceanic floor, and so on. This means Pratt found out that there is an inverse relationship between the height of the relief and their density. So here you can see what Pratt had found out. Density of mountain is less than the density of plateau. Density of plateau is again less than the density of plain, and the density of plain is less than density of ocean floor. So in a single word, the ocean floor is the maximum dense element. And if you close your eyes and try to think, it is a matter of common sense. The density of the huge mountain will have to be low. to keep it standing aloft. Otherwise, the mountain will crumble down if it is of very huge density. So, in reality, Pratt said the density of the mountain is very low, and the density of the ocean floor, which is at the bottom of the ocean, is the maximum, which we have already read in the previous lectures during the Earth's crust formation and etc. So you see, in this aspect, Pratt is going closer to the reality. To prove his point, Pratt also did an experiment. Like Sir George Airy did an experiment with a bucket full of mercury, and he dipped into it iron pieces of varying length. Alright? Pratt did the same experiment, but he did not take iron pieces. He took pieces of different materials of different density, like he took silver, zinc, pyrite, tin, etc. I'll give you the diagram and explain the rest. So here I have drawn the Pratt's experiment. He took several pieces of varying length, but they are of different material. He took silver, zinc, pyrite, tin, iron, nickel, etc. And very surprisingly, he found that his pieces dipped up to a same level into the bucket of mercury, which is very much possible given the several relative densities of these different materials and their weight. They can sink up to a particular level, and this level was named by Pratt as the level of compensation, above which there is a variation in density of the different columns. So from this particular diagram, it is clear that Pratt's concept was uniform depth with varying density. Now if you go back into the lecture, if you see George Airy's diagram that I made, that was uniform density with varying depth, and both of them substantiated their theory with different experiment. Okay, now let's come back to Pratt. Pratt said it was uniform depth. Okay, this is this depth and with varying density, and it was clear from his different materials like silver, zinc, pyrite, tin, they actually have varying density. Now if we try to attach common sense with it and try to match this with the reality, we will see that this is not the case. Here Pratt went wrong. Pratt gave an idea of level of compensation, that is uniform depth, but it is not true. Actually, the mountains will have deeper roots, plateau will have smaller than mountain, and the root of the plain will be smaller than the plateau. But what Pratt did, he gave them a same root, and here Pratt went wrong. So in the end, we can say that Pratt's concept of isostasy was actually based on law of compensation and not the law of flotation. According to Pratt, different relief features are standing only because of the fact that their respective mass is equal along this line of compensation. And it is because of their varying densities. Now we will quickly move up to the next scholars like Hayford, Bowie, Joly and Heiskanen, and we will see that they either agreed to Sir George Airy or to Pratt or to both. Now we will straight away move to the ideas of Hayford and Bowie, and we will see their idea is just similar to the idea of Pratt. They didn't do anything much, only they calculated the depth of level of compensation, and they said that this lies to the uniform depth of 100 km. This is the depth. So Pratt spoke about a level of compensation, right? This is the level, and Hayford and Bowie said that that level of compensation lies at the depth of 100 km. That is it. Now if we try to understand that what is it that these scholars are trying to find, like if I take the example of Sir George Airy, he spoke about root and he said that his roots are going up to varying depth. Now if we speak about Pratt said that there is a uniform level where the crustal materials are getting compensated. And if we see the concept of Hayford and Bowie, they said that this plane of compensation or the level of compensation lies at the depth of 100 kilometer. So what is this that they are trying to find out? I give you a clue. If you have listened to my lecture number 3, where I have given this cross-sectional diagram of Earth, there I have described something called Moho or Mohorovičić discontinuity. You can go back to my lecture and listen to it. It is this Moho discontinuity that they are trying to find out. And this Moho discontinuity is nothing but the discontinuity between the lithosphere. See, this is the lithosphere, this is the mountainous part, this is the plateau, this is the plain, and this is the ocean floor, right? And this whole part is the lithosphere. And this lithosphere is interacting along this Moho discontinuity with the upper mantle. And you see this greenish part is called asthenosphere. And we all know that asthenosphere is a semi-molten layer, and this asthenosphere is a part of upper mantle. So asthenosphere is a semi-molten layer, also called plastic layer, into which this lithospheric plate is submerged up to different depth. You can see here, this is the mountainous column, okay, this is the plateau column. Hope you are remembering George Airy's theory. This is the plain column, and this is the oceanic floor. So this is the oceanic column, and this lithosphere is ending here, and this is the Mohorovičić discontinuity. Now that I have already told you that this is the reality, so you can compare and contrast the several theories that you have read. Like we have read Sir George Airy's theory. Airy has spoken about different routes up to varying depth. So this is true. See, this is the Himalaya, which has the greatest route into deep into the asthenosphere. And then if we take the plateau column, it has smaller route. Okay. Now if we take the ocean bottom, like the basaltic ocean floor, it has the smallest of the route. Okay. But then if we speak about Airy straight away spoke about the level of compensation, and Hayford and Bowie said that that level of compensation is at the 100 kilometer depth, which is wrong, because here only we have seen that the route of a mountain is at a larger depth, which is almost 80 kilometer. In reality, the plateau route is lying at a depth of around 40 kilometer, and the sea floor route is at a depth of around 5 to 6 kilometers in reality, whereas Hayford and Bowie said that the level of compensation should be at a 100 kilometer uniform depth. So there they went wrong. Now if we speak about the density aspect, Sir George Airy said that all this column has the same density, whereas Pratt rectified that. Pratt said that the Himalayan column will have lower density, that's how they are so high and still maintaining the balance, and the plateau column will have higher density than Himalaya, and the ocean bottom will have the densest material. Next, let us shortly describe the theory of Joly. Joly, while presenting his view on isostasy in the year of 1925, contradicted the concept of Hayford and Bowie, because he said that Hayford and Bowie is speaking about a level of compensation at 100 kilometer depth, but in that depth it is not possible to have a crustal material. It will simply melt out. And Joly gave an idea of zone of compensation, okay, instead of line of compensation or the level of compensation. And he said that his zone of compensation is 16 kilometer in thick, and above which the density is the same for all the land masses. So it is very clear that his concept is closer to George Airy's concept, because he is speaking again about a zone of compensation. That is, he is speaking about different depth of the route. Okay. whereas Pratt and Hayford and Bowie speaking about a level of compensation at a same depth of 100 kilometers. But Joly again went back to George Airy's theory. He said there is a zone which is 16 kilometer in thickness. But Joly also said that above the zone of compensation, the density is the same. That is what George Airy said. And in this density aspect, again Joly fell wrong, because the mountain, plateau, plain, ocean bottom, etc. cannot have the same density. They are made up of different minerals. Now last but not the least is the idea of Heiskanen. He gave his theory in 1933 and he borrowed Airy's idea of root formation, that is varying depth. And you can match this, how he is going closer to the reality. See, here you have the varying depths and the root formation. And he also borrowed Pratt's idea of varying density. We all know that in reality the crustal materials differ in their density. Okay, so Heiskanen in 1933 reconciled both the theory of Airy and Pratt. And then in the third point, Heiskanen added that inside the crustal mass or the column, the density actually increases towards the base or the bottom. This is again another matter of common sense. Pratt said that the density is different. Okay, now Heiskanen is adding that how does this density change? The density increases towards the bottom, and we all know if you increase the density towards the base or the bottom, then the crustal architecture will be very stable. So at the conclusion we can see that how the theory of isostasy developed through the work of different scholars. Like first it was Sir George Airy who gave the idea of uniform density with varying depth. Then came Archdeacon Pratt who spoke about uniform depth with varying density, and we see that who was closer to reality and how much. And then came Hayford and Bowie who said that this Pratt's uniform depth is at the depth of 100 kilometer. And then came Joly who again reverted back to George Airy's theory, and he gave the idea of zone of compensation which is 16 kilometer thick. And then at the end comes Heiskanen who did the reconciliation between George Airy and Pratt, right? And that's how in the end we get this real diagram. Thank you very much. Like, share and subscribe.